Okay, folks, this is a continuation of the domain of logarithms, or excuse me, the logarithms introduction that we did in the last video. And in this section, I want to focus on the domain of logarithms. So if you recall, last time we developed the graph of both e to the x, which looked like this, passing through the ordered pair 0, 1 with a horizontal asymptote at y equals 0. And we also developed the graph of the natural log of x, which is its inverse, and as such passes through the ordered pair 1, 0, and looks something like that. That's the graph of the natural log of x. And where e to the x had a horizontal asymptote at y equals 0, the natural log of x has a vertical asymptote at x equals 0. So y equals 0 there. So let's just make sure that this is completely clear. For e to the x, let's give it a name. Let's call it g of x equals e to the x. The domain of this function, through there's many ways we could argue this, but if you look at the graph, the domain of this function goes from negative infinity to infinity. That's the domain. And 0 to infinity is the range, and we can see that as well from the graph. So for some other function, h of x, which would be the inverse of this one, the natural log of x, because of the way we construct an inverse, this is going to have a domain. Let me do that all in blue. This is going to have a domain of what? Well, we can see from the graph, or we can see by the domain range switching when we construct an inverse. The domain of the natural log is going to go from 0 to infinity, and the range goes from minus infinity to infinity. Okay. So let's just tackle some basic questions. Let's say I give f of x is equal to the natural log of x. The domain of this function is what? Well, this is just the natural log function. We were just speaking of this. Its domain goes from 0 to infinity. So if I give you some new function, g of x is equal to the natural log of x minus 3. Let's not do x minus 3. The natural log of x minus 4. Well, the domain of this, well, what? So we are only allowed to plug in positive numbers into the natural log operation. So we need to ensure that the argument here is always positive. So we set x minus 4 to be strictly greater than 0. This is really important. This is strictly greater than 0, not greater than or equal to. Strictly. So this gives us then that x must be greater than 4. So the domain of g goes from 4 to infinity. Okay, let's just do one more like that. If I give you h of x is equal to the natural log of x plus 5, if we set the argument to be strictly positive, then we get that x must be strictly greater than negative 5. So the domain of h would go from negative 5 to infinity. Okay. Let's do two more then. One will be, well, they'll both be a little more challenging. So let's say I give you the function j of x is equal to the natural log of x squared minus 16. So we need x squared minus 16, this argument, to be greater than 0. Well, this is similar then to some of the more complicated radical domains that you did in the last sequence of problems. And what do? Well, we construct a number line, and on the number line we put anywhere where the inequality is 0, or where this inequality, this expression on the left-hand side, is undefined. So this is 0 at x equals 4, x equals negative 4, and it is undefined nowhere, meaning that I can plug any number for x into this expression. So then on the number line I put these two values, the places where it was 0, and let's go ahead and label these as 0. And then what did we do last time we did this? We picked test points. So we picked a test point from inside each one of these intervals. So I don't know, let's pick negative 5, let's pick 0, let's pick 5, and let's plug them into j of x. Okay. Or let's plug them into, excuse me, not j of x, but this inequality right here. So what do we find? Well, if we plug in negative 5, this quantity right here is negative, this quantity right here is negative, and the product of the two negatives is a positive. And if we plug in 0, this quantity is positive, this quantity is negative, so the product of the two is negative. And if we plug in 5, positive and positive, their product is positive. So looking at the inequality, what did we want? We wanted this expression to be greater than 0. Well, we said that for any value we pick in this segment, or any value that we pick in this segment, will return positive numbers. So what's our solution set here? Our solution set is this interval and this interval. So from here we can see that the domain of j goes from minus infinity to -4, unioned with 4 to infinity. These are the values I could plug into this function. Okay. I'm going to do one more. This is a little more challenging. Let's say we had the function k of x is equal to the square root of the natural log of, let's say we have x plus 5. Okay. So this is a combination problem. We now have a lot of stuff happening. Natural logs are problematic. We can only take the natural logs of positive numbers. And square roots are problematic. We can only take the square roots of non-negative numbers. So for the square root, excuse me, for the natural log, let's see, natural log, what do we need? We need x minus 5 to be greater than 0, which means we need x to be greater than negative 5. Okay. But for the square root, we need the argument, the radicand, to be greater than or equal to 0. Well, if we need the radicand to be greater than or equal to 0, that means that the natural log of x plus 5 must come out to be greater than or equal to 0. Okay. Well, this involves us understanding a little bit about the graph of the natural log, which we just looked at. Well, where is the natural log 0? Where does this, so I'm going to analyze this very similar to the way I did the number line before. So I'm putting on where it's undefined. Well, it's certainly undefined for values to the left of negative 5. So let's see, there's negative 5. And it's undefined everything to the left of negative 5. That's what we said here. But where is this expression 0? Well, this expression is 0. Well, let's see here. Let's see if we can analyze this. We want to know when is the natural log of x plus 5 equal to 0. Well, if we convert this to an exponential expression, this would say e to the 0 is equal to x plus 5. But e to the 0 is just 1. So this happens at x equals negative 4. So let's go ahead and put negative 4 on the number line, because this is where the expression came out to be 0. Okay. So then we could take some test points. It doesn't make really any sense to take a test point from in here, because it's not in the domain, but if we say we took negative 4.5, we could plug that into this inequality. And let's take, I don't know, something much easier to work with, say 0. Okay. So if we plug negative 4.5 into this inequality, we'd be taking the natural log of 0.5. The natural log of a number less than 1 is negative. If we plugged in a 0 into the inequality, we'd have the natural log of 5, and the natural log of a number that's larger than 1 is going to come out to be a positive number. So what is the domain of this expression? The domain of this expression, let's return to the original function way up here. K of x is equal to the square root of the natural log of x plus 5 would be, we need values from -4 to infinity. So we can't take values to the left of negative 5 because the natural log wouldn't be defined. But we can't even take values to the left of negative 4 because if we took values to the left of negative 4, then even though we could take the natural log of that expression, we wouldn't be able to take the square root. So, and this should be, this inequality here is a bracket, because we do allow x to be -4, and you can check that. If we look at k of -4, that would be the square root of the natural log of -4 plus 5, which is equal to the square root of the natural log of 1, which is equal to the square root of 0, and we can indeed take the square root of 0. So that's why this is a closed bracket here. I hope that was helpful. If you have any questions, let me know.